Yes, hello everybody. Welcome back. Today I want to talk about static analysis and in particular what intermediate representations have to do in this space and what their purpose is and what is also a particular intermediate representation that you will also be using throughout this course. So let me start by showing you this slide here. So whenever you want to do any kind of analysis of any system that interests you, so for instance, let's say you want to do such a stream analysis here of a car, right, to see how air actually flows across the chassis, then you also would model it, right? I mean, of course, you can also do this live actually and measure how the car actually behaves. But normally you do this, at least in rapid prototyping, you do this through a model. So there are physical models that you can model in a computer, and then you can determine certain properties of that model. Here we also want to do some kind of analysis, but it's a very special kind of analysis. It's a static data flow analysis. That's what this course is all about. But also here we are looking at a particular kind of system, right? We are looking at source code and bytecode, and we want to define or determine certain properties, such as, for instance, a file should always be closed by my program, and so on. And then we also want to evaluate that property, right? So we want to basically be able to automatically iterate through program points and collect data about this property of the program until we have determined it, until nothing changes anymore. Yes, let's take a look at a particular kind of example program. So what you see here, for instance, is just a little example written in Java. It's a small Java method. It's not that important what it does, but what is important is that here you see it's Java source code. And on the right-hand side, what you see here is what we and also others call a control flow graph. So you can see that there's quite a different structure, right? So here we essentially have characters and tokens, and in one way or the other you could also interpret this as an abstract syntax tree. So it's a tree structure, and here we have a graph structure that actually explicitly encodes control flow. So we know by looking at the graph that after this if statement here we could end up at one of these statements, so this line or this line. But after executing any of those, we will definitely get to the return statement. That is somewhat apparent from the abstract syntax tree, but it's not quite as explicit. And in particular, when it comes to looping constructs, such a control flow graph encodes the flow of the control much more explicitly than an abstract syntax tree would do. But in general, the idea is that we always parse such a method and convert it into a control flow graph. And in such a graph, like you see here, the individual nodes, they are simplified statements. They're simplified in the sense that they are not complex statements, so they cannot be compound statements in particular. Every single control flow graph contains a single primitive statement only, that only performs a single operation. That's something that this transformation here must ensure. Then also these edges here, they encode possible control flows between such statements. Why do I say possible control flows? Well, the reason is that control flow graphs, they are usually over-approximative. So let's take a look at this little example program that you see here. So here we have two different conditionals on P and on not P. What you would see in a control flow graph is the following. So we would assume that for the first if then else here, we could take both branches. So either we go to the statement here, so we jump here, or we don't. And the same we would also assume to be true for the second statement. So we would either go to the then branch or we wouldn't. Okay. But if you now look at the program, then you will see that actually both branches are mutually exclusive, right? So assuming a fixed value for P, which is a sensible assumption, you cannot execute both along here and along there, for instance, right? That's just impossible. But in a regular control flow graph for a typical data flow analysis in the style that we will talk about in this course, we assume that these cases are possible nonetheless. So basically these mutual exclusions due to conditionals, they're not being considered. There are certain kinds of static analyses, so-called path-sensitive analyses, that we will briefly talk about. They take care of this, but they're rather exotic. And in most kind of data flow analysis, you would not consider these conditionals. And that makes also sense to some extent, because depending on how complex this predicate P is, you cannot actually possibly infer that these branches are mutually exclusive. So let's assume that P actually looks like this, right? So here we have one conditional that checks whether this is a prime number, and we have one other conditional that checks whether that is a prime number. And I'm not sure who of you could immediately tell me which is a prime and which one isn't, and if both are primes or if they're both not, right? And so you can imagine if you have such a program with an arbitrarily complex condition, then also for a static analysis, it would be very hard or often even impossible to figure this out. And therefore, most program analyses, they don't even try. So they simply assume that both cases are always possible. So basically, the guarantee that you give is that you get is that if control may flow from one statement A to a statement B, then there is an edge from A to B. So that is the guarantee that you should get. People also say that the control flow graph then is sound, so it's correct. It models at least the control flow that is possible in your program. But the opposite is not true, right? So you can have edges in your control flow graph that are never actually taken at runtime. And this problem you can never really solve in full. It's an undecidable problem. I wished, as many people do, that there was a 100% solution, but it has been shown since a long time that that's actually impossible. And real-life control flow graphs, they will even contain edges for exceptional control flow to be sound. So for instance, if you're looking at a Java program that is doing some arithmetic, let's say it's dividing two numbers, then if the one number is 0, you get a division by 0 exception. And then there would be a control flow edge in the control flow graph that models possible flow to the exception handler that is actually catching that particular kind of exception. An important design decision when you're building control flow graphs is which nodes to allow and which ones not. And there are different choices here, and I want to talk a little bit more about this. One extreme could be that you are actually allowing any statement that can occur in Java source code, right? And there are actually static analyses that operate directly on source code. So what you see here, for instance, it's a mock-up of what you would see in your favorite IDE, such as Eclipse. If you insert such Java code here, that is accessing a possibly undefined value, such as x, which is defined in this branch but not in this branch, then Eclipse will actually give you an error message here highlighting x, telling you that this value is undefined. And that is an analysis that is actually being conducted on a control flow graph abstraction, but a very simple one over the abstract syntax tree. So essentially, it's directly operating on source code, you could say. The problem is that this becomes very complex if you have complex code. And in Java, and then also in other languages, you can have quite complex code. So you can have nested statements like you see here, for instance. Then also you can have even new objects being created in such loops here. And in Java in particular, you can even create new anonymous inner classes like you see here within any expression, within any statement, within any loop. And then it's not quite so apparent how control flows here, right? So is this compare to method actually called within the loop? And if so, when is it called, or is it only defined here? Even for programmers who are not Java experts, that might be hard to tell. And if you have to program the logic to create a control flow graph out of this, it's not quite so much fun. Another extreme would also be Java bytecode. You could also decide to directly analyze bytecode. So this also has some advantages. For instance, there is no nesting. So in Java bytecode, you cannot have any nested statements. One statement directly follows the other. And also looping and branches, they are all modeled in the same way, basically through goto statements. You can have conditional and unconditional gotos, that's it. But there's no while loop construct, for instance, or for loop in bytecode. That doesn't exist. Also, nested classes like I showed you, also these anonymous inner classes, they are flattened into normal classes. So to the Java virtual machine or anybody else processing Java bytecode, they all look the same. They're just regular Java classes. But there are also some disadvantages. So for instance, in Java bytecode, you know nothing about local variables. So basically there are no local variables. Operations that you would normally perform using local variables in bytecode, they are performed using an operand stack. And I'll be showing you an example in a second. And another disadvantage is that there are more than 200 possible bytecodes. So that's quite a bit. Essentially, that means if you are processing bytecode directly with your static analysis, that whenever you are processing a single statement, there are 200 different cases that you need to consider. And that just makes for a bit of a convoluted analysis implementation if you are not careful. So let me show you a little bit in more detail what challenges you might have in this space. So here we again have some Java source code, and it's doing something very simple. It's taking two doubles, multiplying them, casting them to an int, and passing the result to a procedure call. On the left-hand side, you now see a dump of the Java bytecode for that particular method. And let's look a little bit through this, what's happening here. So here we're basically loading two constants onto the stack. And then we are actually loading them into given registers. So 1 and 3 are registers. And then here, these are loaded again onto the operand stack. And then you have this demul instruction here. And what this is doing is the following. So it's basically taking these two operands that have been loaded onto the stack. It's popping them off the stack, it's multiplying them, and it's at the same time putting the result of this multiplication on the stack again. Then we have another operation further down here that's actually taking this result and casting it to an int. Then that's being stored. Now, what you see here is that there are many overloaded versions of essentially the same operation. So here we have, for instance, instructions that are actually operating on doubles. Here we have instructions that are operating on integers and on objects. So this A load, for instance, that's an object instruction. And everything that starts with an I, that's regarding integers. So you have instructions that do load and store, but they are they are distinguished based on their data type, although they all do the same. So that means if you do a static analysis on this kind of code, it must distinguish between a D load and an A load and an I load, although essentially they are all performing the same operation. So it's increased work, although the semantics of all of these statements is essentially the same. Also, because we have this operand stack here, that makes it a little bit hard to determine what's going on here, right? So if you, let's say, you only look at this one line of code here, right? This demul, you see that something is being multiplied, but by looking at this single line, you cannot really tell what is being multiplied. In order to do that, you actually have to look backwards into the previous stack operations, and the last load onto the stack, it might not be directly preceding this multiplication, right? So in this code here it is, but this load might also be further up, and the code might be interspersed with some other instructions. And then it's really hard to tell what this operation really does. So that's why analyzing a stack-based bytecode is really not fun, and it's usually something that people try to avoid. That's also being, so the problem is made worse because there are also different kinds of bytecode, right? So you can also have Android bytecode, for example, not just Java bytecode. And Android bytecode is relatively similar, but it's not quite the same again, right? So here, for instance, you don't have an operand stack in Android. You have local registers that sort of model somewhat closely the local variables that you would see in source code. Then also you have some values that are untyped, and that's something you again don't have in Java, and that makes analysis hard nonetheless. So for instance, you can have numerical constants in Android that are simply being used at a certain point in the program, but until they are being used, you do not know their type. So for instance, if you see the value 0 in Android bytecode, you cannot really tell just by looking at it whether it really means 0 as an integer or 0 as a float, or for instance also null, so the pointer value. So only at the place where it's being used, it's sort of implicitly casted to the right type. Yeah, that also makes for complications in the analysis. Then also you have many Android bytecodes, so it's even more than in Java, roughly 250 of them. Which also makes the problem of analyzing Android bytecode directly even harder as well. So to summarize all of this, so we don't really want to generate a control flow graph directly based on source code, right? Because like I said, these statements can be too complex, and that wouldn't really be much fun. We don't really want to operate on Java bytecode either for the reasons I outlined. And therefore the idea is that we really want to go, we still want to go to a control flow graph, but we want to have one based on a so-called intermediate representation. So here we will have simple control flows, that's one requirement, and we will have a low number of operands. That's another requirement that we have. And so what I want to talk about today as the last part of this week is the so-called Jimple intermediate representation, which is the primary intermediate representation of the SUIT static analysis framework that we will also be using in this course. So like I said, you will be having the option to use either SUIT or Phasor. Phasor has a slightly different intermediate representation. It's a little bit more low level, but essentially it shares a lot of the ideas with Jimple. So a lot of what I will be telling you about Jimple will also be true for the LLVM intermediate representation that Phasor uses. Jimple is an intermediate representation tailored to Java, for Java programs, and that's also an explanation for its name. So Jimple basically stands for something that is like Java, but it's simple, and it's simpler than Java. And the idea is that it combines the best of both worlds, so of both source code and bytecode. In particular, it does have local variables like in source code, so there are no stack operations that you need to deal with. That means every single statement directly declares what kind of operands it's operating on. That makes the analysis simpler. Also, there are special variables that are generated for the this object, and also for parameters that are passed to methods. So essentially that means in Jimple they are also modeled through local variables. And so there's one unified way of dealing with all of these values. Also, there are only simple statements, so just as in bytecode, statements can never be nested. Let's take a look at what this looks like. So here on the right hand side we have the same source code that I showed you earlier with the very same operations. But here on the left hand side I'm showing you now not Java bytecode, but the Jimple representation that we would get out of this. What you will first see here is that you have this leading block at the top that explicitly declares all the local variables that are relevant in this procedure foo that we see here. And you will also see that all variables are really explicitly declared. There's even this special variable that you see here, which is called this, And this is actually the local variable that we will later on be using to represent this object that always implicitly exists in instance methods in Java. This variable here, it becomes special by assigning it this very expression that you see here. So this expression on the right-hand side, the one with the @ this signals that we want to initialize that variable here with the this object. So that is loading the this object. It's basically falling from the sky, right? So it's in Java, it's always implicitly there. But here we are explicitly assigning it to that variable. And here the name of this variable is really this. It's THIS. But I could also have named it something else, right? So the name is not important. What is important is that it has been assigned this expression here, and therefore it's pointing to the this object. And then later on, when we are calling a method on this, like you see here, then this is actually done using that particular variable here, right? So that's what I meant earlier. So everything that's happening in Jimple, it's happening explicitly on these local variables. And just the same here, this is just a local variable that has been initialized appropriately. And this method here is being called on this object. What you see also here is that there are no stack operations, right? So you don't see any of this demal or so. You have these explicit assignments and explicit calculations that you see here that explicitly reference the operands that they are operating on. And that's a very nice feature because basically everything is now explicit and not implicit anymore. And just by looking at a single statement such as the multiplication, you can directly see which operands are involved. Another difference is that complex statements are broken down, right? So that's a difference to source code. And if you look at this source code line here, then it is a little bit of a complex statement, right? So essentially, this statement here is doing two operations at the same time, or actually one after the other. So first we're doing a multiplication here, and then the result is being casted and then assigned to this variable, right? And that's what's happening here in two different statements, right? So in the first statement, we are doing the multiplication, and it's actually being stored in a temporary variable. And then the result of that multiplication, it's actually casted and stored in the original variable that it was supposed to be stored into. So this variable I1. What you also can see here is that Jimple does contain these temporary variables, and they get automatically generated to basically represent these stack locations that you would otherwise have implicitly in Java bytecode, right? And you can see these temporary variables, also you can identify them by their name, because typically in Jimple they will carry this $sign. That is just a convention. You cannot always 100% rely on it, but usually it's a good rule to keep in mind, and you should also obey to this rule if you generate Jimple code on your own, so that you can always easily identify these variables. In Java source code, you cannot have a $sign and an identifier, so you could not possibly declare a variable that clashes with this convention. One important point I still want to make is in Jimple and also all other similar intermediate representations, typically operations look like this. So you have two operands typically on the right-hand side and one operand on the left-hand side. And therefore, this kind of code, this kind of intermediate representation is also called a 3-address code. So you have 3 addresses that are being referenced, this one, and this one. There are exceptions, like this statement here, that's only operating on 2 addresses. If you have a procedure call that can also operate on more addresses, depending on how many parameters you have. But still, you would call this a 3-address code. Another important point is that method calls, they are always fully resolved. So for instance here, you see that bar is called on something, but you don't really know on what. You have to have implicit knowledge about this. But here you know that it's being called on this. And you also know that it's the bar method declared within a class called main. You couldn't see this just by looking at the method here because it's also implicit from the class name, but it is implicit in this method call reference that you will see in Jimple code. So to summarize that again, in bytecode, each instruction has an implicit effect on the stack, whereas in Jimple code, each statement acts explicitly on named variables. In bytecode, you have no types for stack locations, and in Android bytecode, you wouldn't even have types for certain constants. And in Jimple, you have types for all local variables and also for all constants actually. In bytecode, you have more than 200 kinds of instructions, which makes the analysis more complicated. Whereas in Jimple, you actually only have 15 different kinds of statements. So that's really not a lot, right? So 15 kind of cases to distinguish in a static analysis, that's something we can do. So let's look a little bit more into what kind of statements these are. First of all, we have a number of core statements. So you can have a NOP statement, which is maybe the most boring statement that you can think of because it does nothing at all. Why is such a statement useful? Well, sometimes when you generate Jimple code out of other sources, you also have to generate loop constructs, for instance. And then you may find yourself in a situation where a loop or an if then else or so has to jump to a statement that has not yet been generated. And then you can sort of generate a NOP statement as a placeholder, and that you can use as a jump target, yeah, that makes code generation more simple. Then you can also have definition statements, and they can have two kinds. So you can have a so-called identity statement, and that is the kind of statement we saw that is assigning these at expressions. So it's assigning the this value, for instance, but it can also be assigning a parameter value to a local variable. If you are assigning something else to a local variable, then this is done using a regular assign statement. Then we have statements that care about intra-procedural control flow. So control flow happening within a procedure. And this is an if statement, which is basically a conditional goto. So it defines a certain expression, and if that expression is true, then it jumps to a certain statement. If that expression is false, then you simply continue with the next statement. Then we also have a goto statement, which always jumps to a certain target statement. And then we have certain switch statements, which you also know from the Java source code language. In Java bytecode, due to certain implementation details, they actually distinguish between a so-called table switch and a lookup switch. And for convenience reasons, it was decided that you actually have the same kind of two switch statements also on the Jimple level. There might be a way to simplify this, but currently the way this is defined in Jimple, you have these two kinds of switch statements to deal with. Then there's also inter-procedural control flow, so control flow between procedures. And this is done through an invoke statement that invokes a procedure, through a return statement that returns from a procedure with returning a value, and we have a return void statement that does not return a value. Then there are throw statements, which are used to throw exceptions. They basically have the same semantics as you know from source code. Then there used to be red statements, which you should not be seeing anymore in Java bytecode nor in Jimple. So there are older variants of the Java compiler, Java C, that still generated them to deal with exception handling. But it was very early on discovered that this was not a good language design, and it complicated bytecode validation and also the execution of the bytecode. So therefore, current compilers don't generate these bytecodes anymore, and also Jimple code therefore does not contain this anymore. But what you do still see are so-called monitor statements. So there are two kinds, an enter monitor statement and an exit monitor statement. And these mark basically the beginning and end of synchronized blocks that you see in Java. So whenever you enter such a block, you will see this statement. Whenever you exit a block, you will see a corresponding exit monitor statement. And so the idea is here that we will first convert Java source code, or actually also Java bytecode. For suit, it doesn't matter. You can convert them both into Jimple IR, like you see here. And then we will have a control flow graph over Jimple statements. So each individual statement that you see in the control flow graph here, this is not a Java source code statement anymore. This is now a primitive Jimple statement. So basically, you could say a line of code in this representation that you see here. So you could have a node for basically such a goto here, or such an assignment here, or such an identity statement here, but you could not have any node for any compound statement. They cannot be any more complex than that. And because you here have explicit gotos, like you see here, or an if, for instance, like you see here, this directly translates into these control flow graph edges that you see on this level. So really the Jimple IR directly encodes a control flow graph. There's a one-to-one correspondence between every single line of code here and one or more edges that you see in this graph here. It's a very simple translation. To summarize, in general, intermediate representations, they can abstract from concrete input languages. So, like I showed you here, at least to some extent, the Jimple IR, it can represent Java source code, it can represent Java bytecode, and it can even represent Android bytecode, and we now even have a front end for Python source code. So all of these languages, in one way or the other, can be translated to the Jimple IR. For some languages, that might be simpler than for others. For some languages, the translation might be more direct than for others. For Java, it's particularly direct. But for many of these languages, it's possible. And this is nice, because once you have then written an analysis that can operate on the Jimple intermediate representation, you can apply it to any program written in any of these representations, in any of these languages. So we can use suit, for instance, to analyze Java bytecode and source code, and also Python programs. Jimple is an intermediate language in 3 address code format, like I explained, right? So it has this property that it has only these simple statements. Also, most things are really explicit, like I explained. Every statement is atomic, there is no nesting, and this therefore simplifies the notation of flow functions that I will be showing you later. So a flow function is basically sort of a primitive that you have in your static analysis that defines what's happening when the analysis is processing a single statement. And the more simple your statements are, and the fewer kinds of statements there are, the more easy it is to define these kinds of flow functions. And that's what we will be covering in the next week. So in the next week, we will be talking about intra-procedural static analysis. And that basically means we will have the following situation. So we will be given as input a method, like you see here, or a procedure or function, and also a property that we want to determine over this method. And then I will tell you about different ways in which we can determine whether this property holds or does not hold at any given statement in that method. And there are different ways to do this, and one particular way is to do this using so-called type systems, and this is what we will be talking about first in the upcoming week. That was it for this week. Thank you very much for your attention, and I will see you then. Bye-bye.